As we continue to develop the theoretical foundations of relativity, it's important to be comfortable with the manipulation of tensors. In this lecture, I want to review the mathematics and notation and introduce new terminology along the way. So let's begin with x mu. The x mu are coordinates. So these are four scalar functions on space-time. So the index mu labels those four functions. So mu takes on values 0, 1, 2, and 3. And in particular, x mu are not the components of a vector. A vector is a derivative operator, so it acts on functions, and when it acts on a function, at each point in the spacetime it produces a number. So it maps a function to a number, or if we're talking about a vector field, it maps a function to a function. So if V is a vector, we can always expand it in a linear combination of basis vectors. So here, V mu are the components of the vector, and d by dx mu are the basis vectors. So the action of a vector on a function is just V mu partial phi with respect to x mu, if phi is the function. Now a covector is an operator that maps vectors to numbers or functions. A single covector at a point will map a vector to a number. A field of covectors will map a field of vectors to a function. If W is a covector, we can always expand this covector as a linear combination of basis covectors. So here W sub mu are the components of the covector, and dx mu are the basis covectors. How does the covector W act on a vector? Well, if the covector is the differential of a function, then W acting on a vector V is just defined to be the number obtained when V acts on the function phi. So we can use this to determine how the basis covectors, say dx mu, acts on a basis vector, d by dx nu. So according to this rule, this is the differential of a function x mu. This is just equal to partial with respect to x nu of the function x mu. And that's just Kronecker delta mu nu. If we have a general covector W acting on a general vector V, we can compute this by expanding W as a linear combination of basis covectors and expand V as a linear combination of basis vectors. And now dx mu acting on the vector d by dx nu just gives the Kronecker delta. So this is W mu V nu times Kronecker delta mu nu. And in the sum over the index nu, every term is 0 in that sum unless nu is equal to mu. So this is equal to W mu V mu. We can see from this result that the action of a covector acting on a vector can be expressed in terms of the components of the covector and the vector by just simply wiring the indices together like this. Now, a couple of results that are worth keeping in mind is that whenever we have a basis covector acting on a general vector, this is just equal to the components of the vector. So you can see this by expanding V as a linear combination of basis vectors and letting dx mu act on the basis vector to give a Kronecker delta. The result is V mu. And similarly, if we have a general covector acting on a basis vector, the result is just the components of the covector. Now let's turn our attention to tensors. A vector, which we can always write this way, is a type 1,0 tensor. And the meaning of 1,0 is that this is an object that can be acted upon by one covector. A covector, which we can write this way, is a type 0,1 tensor. And the meaning of 0,1 is that this is an object that can act on one vector. A type NM tensor is an object that can be acted upon by n covectors, and it can act on m vectors. As an example, let's consider a type 1,2 tensor. We'll call it T. T can be expanded as a linear combination of basis vectors and covectors. So this is T mu alpha beta dx alpha outer product or tensor product with dx beta outer product with d by dx mu. This tensor can be acted upon by one covector and it can act on two vectors. So let's denote the covector by W, so that can act on T, which can act on two vectors. Let's call them V1 and V2. So this is T mu alpha beta. V1 is acted upon by dx alpha. V2 is acted upon by dx beta. And W acts on d by dx mu. Right? If we remember, this is just the alpha component of V1. This is the beta component of V2. And this is the mu component of W. By the way, you should notice that the outer product is not commutative. So the order does matter. So in this example, I put V1 into the first slot of T, and that meant it was acted upon by dx alpha. And V2 going into the second slot meant it was acted upon by dx beta. And so that gave us this result. If I had accidentally put V2 into this, let it be acted upon by dx alpha, and V1 be acted on by dx beta, then these two factors would have been reversed. This would be V alpha 2, V beta 1. And that's not the same thing unless this tensor happens to be symmetric under interchange of alpha and beta. But for a general tensor that's not symmetric, the order does matter. On the other hand, the placement of this factor d by dx mu doesn't really matter in this example. I could have written d by dx mu in front of dx alpha and dx beta. The only thing that W can act on is the d by dx mu factors, so that's unambiguous. On the other hand, if this were, say, a type 3,2 tensor, there would be three factors of d by dx mu, and we would have to keep the order straight. So when we acted upon that tensor by three different covectors, we make sure that we let each of those covectors act on the appropriate basis vector, because the order does matter. So for the outer product, the order among the basis covectors matters, and the order among the basis vectors matters, although the order between basis covectors and basis vectors is irrelevant. So a type NM tensor can be acted upon by n covectors, and it can act on m vectors, but we don't have to let all this action occur at the same time. So for example, for our 1,2 tensor, we can let a covector act on that tensor. This is W acting on T mu alpha beta dx alpha outer product dx beta d by dx mu. But W acting on d by dx mu just gives the muth component of W. So this is W mu T mu alpha beta dx alpha outer product dx beta. So what we've done is we've constructed a type 0,2 tensor from the type 1,2 tensor by combining it with this covector W. In a similar fashion, we can let T act on a single vector, but now I need to be careful because it matters which slot I put that vector into. Let's say we put it into the second slot. So this would be T mu alpha beta dx alpha tensor product dx beta tensor product d by dx mu acting on the vector v, and it's acting on the vector v in the second slot. So that means it's the dx beta covector that's acting on the v. So this, of course, when it does so, it just gives the beta component of v. So this is equal to T mu alpha beta v beta times dx alpha tensor product d by dx mu. So what we've done here is we've created a type 1,1 tensor from the type 1,2 tensor by filling one of those slots with a vector v. Notice the notation here is not very good because without the arrow you wouldn't know which of these factors, dx alpha or dx beta, were acting on the vector v. And I would also have a similar problem here if I'd used the more standard kind of notation of just t parenthesis v. You wouldn't know which of the two slots on t the vector v was being inserted into, so this is ambiguous notation. On the other hand, this index notation is completely unambiguous. The wiring together of these indices, this repeated index beta, shows that the vector v is being placed into this second slot on the tensor t. So usually, if we want to denote the result of say, a type 1,2 tensor like t acting on a vector v in its second slot, we simply write that as T mu alpha beta v beta, and we don't bother to write these factors of dx alpha outer product d by dx mu. Let's look at another example. Let's take t once again to be a type 1,2 tensor, and let's take another tensor m that's type 2,0, and let's consider T mu alpha beta m alpha beta. All right, what does this represent? We can think of this as t acting on m, so that's T mu alpha beta dx alpha outer product dx beta outer product d by dx mu acting on m sigma rho d by dx sigma outer product d by dx rho. And now we have to decide how this tensor is going to act on this tensor. If we let this covector factor act on the first vector factor here and dx beta act on d by dx rho, then what we obtain is T mu alpha beta. Let me write these coefficients first. M sigma rho. Dx alpha acting on d by dx sigma gives Kronecker delta alpha sigma. Dx beta acting on d by dx rho gives delta beta rho, and then we're left with this factor of d by dx mu. This is equal to T mu alpha beta times m. Now in the sum over sigma, the only term that survives is when sigma is equal to alpha, and in the sum over rho, the only term that survives is the one in which rho is equal to beta times d by dx mu. So we see that this is just the components of this vector obtained by combining t and m. But also notice in order to obtain this result, I had to assume that the first dx factor here acted on the first d by dx factor here. What if I had decided the other way around, to let this first factor act on this second d by dx rho and this second factor act on the first? Let me draw a second set of arrows here. In this case, we would have we would reverse sigma and rho, so that would reverse these two indices, and we would have T mu alpha beta m beta alpha d by dx mu. So these are, of course, both vectors, but they're not the same vector. So you can see that this notation is ambiguous because it depends on how I decide to draw the arrows. And likewise, this notation is ambiguous. On the other hand, if we just look at the components and how they're wired together, that's completely unambiguous. So by focusing on this index notation, we can start putting tensors together in ways that would be difficult to denote otherwise. So for example, let's let T once again be a type 1,2 tensor, and let's take a type 1,1 tensor N. We can form a tensor as T mu alpha beta N alpha mu. So this is a covector, or these are the components of a covector. And I can tell because the one free index is beta and it's down. So that's the components of a covector. And what is this? Is this T acting on N, or is it N acting on T? It's really a little bit of both. It's really the covector part of N acting on the vector part of T, and this first slot covector part of T acting on the vector part of N. So there's not really a good notation for it, but in terms of the components, it's very simple and clear. So two of the most important tensors we've encountered so far in these lectures are the metric tensor, which is a type 0,2 tensor, and the inverse metric, which we just denote with the same base letter G, but just raise the indices. This is a type 2,0 tensor. And G upper mu nu being the inverse of G lower mu nu means that G mu nu G nu sigma is equal to Kronecker delta mu sigma. And what is the Kronecker delta? It's the components of a type 1,1 tensor, which is the identity tensor. One of the things we can do with the metric is let it act on a vector to produce a covector. Or more generally, we can let, for example, if we have a type 1,2 tensor, T nu alpha beta, we can let G act on that to produce a type 0,3 tensor, and we'll denote that type 0,3 tensor with the same base letter T. So this would be T mu alpha beta. And similarly, we can use the inverse metric to change covectors into vectors. So for example, we could write G mu alpha T nu alpha beta, and using the same base letter, we can convert this alpha to a mu. So now this is a type 2,1 tensor. Let me point out a couple of interesting features of this notation. Whenever we have G or G inverse acting on a tensor T, we just use the same base letter T and move the index up or down, as the case may be. So let's look once again at G mu nu G nu sigma. This is G, the metric, acting on a type 2,0 tensor. So by this naming convention, we should use the same base letter and just move this index nu to a lower index mu. So this is G upper sigma lower mu. But we previously said that's the Kronecker delta, right? Because G upper with upper indices is the inverse of G with lower indices. So which is the correct notation? A similar ambiguity in notation occurs if we let the metric act on the Kronecker delta. Right? So by our naming convention, we use the same base letter delta and We use the metric to lower this index mu and nu and turn it into a mu, and then we have the index sigma. On the other hand, we know there's a sum over this repeated index nu, and the only non-zero term in the sum is when nu is equal to sigma, so this is equal to g mu sigma. So what is this? Do we call it delta mu sigma or g mu sigma? Well, either notation is fine here, but the usual practice in relativity is when the indices are one up and one down, we use the Kronecker delta symbol, the delta. And when both indices are down or up, then we use the G, the metric symbol. Here's another situation that occurs fairly frequently. Let's say we have a type 2-0 tensor, call it M, and let's look at G mu nu, M mu nu. In this case, we have both indices on G wired with both indices on this tensor M. But we can view this as, let's say the second index here is wired with the second index here. So focusing on these indices, we have the same base letter, and then we use G to replace this upper index nu with the lower index mu. Remember, there's a sum over the repeated index mu, so if we think of M with one upper and one lower index as a matrix, then this is equal to the trace of that matrix of M, say alpha beta. And this process of setting two indices equal to one another so that they're summed over is sometimes called index contraction. For another example of index contraction, let's take our type 1-2 tensor T and let's contract on the upper and the first lower index. And we do that using the Kronecker delta, delta mu alpha. So this is equal to T mu mu beta. And there's contraction on these two indices. I'd like to spend a little bit of time now putting all of these ideas together and examining a tensor equation. So this is just an equation relating tensors. So let's just make one up. For example, let's take T mu alpha beta, our type 1-2 tensor, and wire it together with type 2-0 tensor M, and that's equal to a vector. So let's just call the vector V. So this is a typical tensor equation. And notice that there are two types of indices. There are free indices like mu. So mu is called a free index. And free meaning it's free to take on any value, 0, 1, 2, or 3. So this is really four equations, one for each value of mu. And the indices alpha and beta in this term are repeated indices. So there are two appearances of alpha and two appearances of beta. So that means they're summed over. So really this is a sum over alpha equal 0, 1, 2, and 3, as well as a sum over beta from 0 to 3. But by the Einstein summation convention, we usually don't write the summation sign. So you should notice that the rules for a valid tensor equation is that the free indices must balance, meaning the free indices are the same in each term, and consistently either up or down. So it wouldn't make sense to have an equation that looks like this, because this is equating the components of a vector to the components of a covector. So the indices always have to be consistently up or down. And the second rule is for repeated indices, in each term, the repeated indices occur in pairs, one up and one down, because it always represents a covector acting on a vector, or a covector component of a tensor acting on a vector component of a tensor. Of course, we can write a tensor equation in lots of different ways. So let me repeat this expression. We have T mu alpha beta m alpha beta equals V mu. Because mu is a free index, it's just a placeholder for 0, 1, 2, or 3. We could also write this as T nu alpha beta m alpha beta equals V nu. As long as the free indices are balanced in each term and consistently up. It's the same equation. And likewise, we have a repeated index alpha here, which just stands for a sum from 0, 1, 2, and 3. So we could write this as, say, T nu sigma beta m sigma beta equals V nu. This is the same equation. These are all the same equations. We can also raise and lower indices using the metric. So for example, let's take this expression and multiply by G mu nu T nu sigma beta m sigma beta equals G mu nu V nu. All right, now the G replaces this index nu with a lower index mu. Likewise here, it replaces the upper index nu with a lower index mu. So this is the same equation, the same tensor relationship. And of course, in this expression, we're free to change the index mu to an index nu, as long as we do so consistently in every term. So this is T nu sigma beta m sigma beta equals V nu. And now if you compare these two versions of the same equation, you can see that the only thing that's happened is the index nu has been lowered, and we refer to that as lowering the index. Another thing we can do is the following. Let's look at this version of the equation, and let's write T mu sigma beta as T mu sigma, I don't know, say rho G rho beta. So here I'm using G to lower the index on rho and turn it into a beta. And this is multiplied by m sigma beta equals V mu. So now we can use this G to lower this index beta and turn it into a rho. So we can write this as T mu sigma rho m sigma rho equals V mu. So you can see here what's happened going from this expression to this one is we've just toggled these indices. In fact, to make it more clear, let me replace this repeated index rho with a beta. So we've just toggled the repeated index beta, moved the one that's down to up and the one that's up to down. So there are lots of different ways that a given tensor relation can be written, like this one, with different choices of index names and different patterns of indices up and down. But you'll notice that the common thing in all of these ways of writing this tensor relation is that the first index on T is the free index, and that corresponds to the free index here on the right-hand side of the equation. And the second and third indices here are wired together with the second and third indices of M. So that's true in all of these cases. And we do need to be careful in writing these different tensor relations, moving indices up and down, that when we do move an index up or down, that we keep it in the same order. For example, in all these different ways I've written this tensor relation, you'll notice that I always keep the free index on T as the first index. So even when it's the lone upper index, I left a gap here. So it's clear that this is the first index, second index, and third index. And that way I can move these indices up and down and make sure that I keep them in the same order. Likewise, for this tensor M, when I lowered this index beta and converted it to a rho, I left a little gap here to remind myself that this is the second index. And if I hadn't left that gap there, if I had written this as m sigma rho, and then later on wanted to move this index back up, it would be easy to make the mistake of moving it up again and then getting the order reversed. And it doesn't matter if m is a symmetric tensor, but we'll often work with tensors that aren't symmetric, in which case the order of the indices does matter. One example where it's very important to keep the order of indices straight is the Riemann tensor, which defines the curvature of the space-time, and it was introduced in the last lecture. The Riemann tensor was introduced as a type 1,3 tensor and written as r mu nu alpha beta. And there's a little gap here because there will be situations where we want to lower this index and we want to be consistent about where it's placed. And the standard convention is that this upper index is considered the first index. So when we lower it, it goes before the other three indices. Now let's take a few minutes to review the covariant derivative. The covariant derivative maps a type nm tensor to a type nm plus 1 tensor. And we can let the covariant derivative act on any tensor or any tensor equation. So for example, let's take this familiar equation, t nu alpha beta m alpha beta equals the vector v nu. We can let the covariant derivative act on this. And now we have a type 1,1 tensor on each side. Here there are one free upper index, one free lower index, so this is type 1,1 tensor. We can use the product rule. This is del mu t nu alpha beta times m alpha beta plus t nu alpha beta del mu m alpha beta equals del mu v nu. We can contract indices, for example, on mu and nu, so we can multiply both sides of this equation by Kronecker delta upper mu lower nu and wire those two indices, the two free indices, together. So this would become del mu t mu alpha beta times m alpha beta plus t mu alpha beta del mu m alpha beta equals del mu v mu. We can raise and lower indices. So for example, returning to this equation, we can raise this index mu by multiplying by the inverse metric and wiring one index to the index mu, and we would have del mu t nu alpha beta m alpha beta equals del mu v nu. We can also raise and lower indices inside the covariant derivative. So for example, this equation is equivalent to del mu t lower nu alpha beta m alpha beta equals del mu then v lower nu. So how do we get from this expression to this one? Let's take a quick look at that. We multiply this equation by g, say sigma nu, and that's equal to g sigma nu del mu v nu. And now let's just look at the right hand side. We can pass this factor of g inside the covariant derivative precisely because the covariant derivative acting on the metric vanishes. So recall del mu g alpha beta is 0. Also, covariant derivative acting on the inverse metric is 0. And also, of course, del mu acting on the Kronecker delta is 0. And it doesn't matter whether the index on the covariant derivative is up or down. That's just, again, multiplying by another factor of g to raise that index. So we can use these results to just pass this factor of the metric inside the covariant derivative. Write this as del mu acting on g sigma nu v nu. And of course, this is just v lower sigma. And we can do the same thing on the left-hand side here. We can bring this G sigma nu inside and lower the index on T. This would become T sigma alpha beta M alpha beta. And now we have the result we want. We just need to rename this free index sigma to nu. And we have this result. Another property of covariant derivatives is that they don't, in general, commute. So del mu, del nu, in general, is not equal to del nu, del mu. So it's true that acting on a scalar, so if I have a scalar function phi, then del mu, del nu on phi is equal to del nu, del mu acting on phi. But when two covariant derivatives act on a vector, they don't commute. So for example, del alpha, del beta acting on v mu minus del beta, del alpha acting on v mu is not equal to 0. And in fact, this is equal to the Riemann tensor r mu nu alpha beta times v nu. And we have a similar result when two covariant derivatives act on a covector. So del alpha, del beta, say w nu, a covector, minus del beta, del alpha, w nu, is equal to minus r mu nu alpha beta w mu. My final goal for this lecture is to introduce the Leviathan tensor. It will be helpful to begin with a short discussion of the identity tensor. So the identity tensor is the tensor with components delta mu nu. This is the Kronecker delta. So it's equal to 1 if mu is equal to nu and equal to 0 if mu is not equal to nu. And this is a rather unusual way of specifying a tensor by giving numerical values to its components, because you have to wonder which coordinate system does this tensor have these values, and does it have different values in another coordinate system? And of course the answer in this case is that the identity tensor has these components in any coordinate system. And we can show that by considering the transformation rule for a general tensor. So let's take a tensor T with a bunch of upper indices mu1, mu2, and so forth, and a bunch of lower indices nu1, nu2, and so forth. And how does this transform if we change coordinates from so our original coordinates x mu to new coordinates, say x bar mu? Then in the new coordinates, the tensor will have components t bar, mu1, mu2, and so forth, nu1, nu2, and so forth. Given by the following expression, we'll have factors of partial x bar with respect to x, and let me use an index, say alpha 1 here. We'll have, for each of these upper indices, partial x bar of mu2 with respect to x alpha 2, and so forth. We'll have a series of factors for these lower indices. This will be, for example, partial x beta 1 with respect to x bar nu 1, partial beta 2 with respect to x bar nu 2, and so forth. All of this times t alpha 1, alpha 2, and so on, and lower beta 1, beta 2, and so forth. So this is the relationship between the components of the tensor in the unbarred coordinate system to the components of the tensor in the barred coordinate system. And if we apply this tensor transformation rule to the Kronecker delta, so if we say these are the components of delta in the unbarred coordinate system and ask what are the components of delta in the barred coordinate system, we find the following. We'll have delta bar mu nu is equal to one of these factors, partial x bar mu with respect to x alpha, And one of these factors, partial x beta with respect to x bar nu times the components of the tensor in the unbarred coordinate system, delta alpha beta. Right, but delta alpha beta has components 1 and 0 depending on whether alpha is equal to beta. So this is just partial x bar mu with respect to x alpha, partial x alpha with respect to x bar nu. But by the chain rule, this is just partial x bar mu with respect to x bar nu, which is just 0 or 1, depending on whether mu is equal to nu. So it's 1 if mu is equal to nu, 0 otherwise. So we can see that in any coordinate system, the components of the Kronecker of the identity tensor are just what we call the Kronecker delta, 1s and 0s. The Levi-Civita tensor, like the identity tensor, can be defined by giving it values to its components. And we can show that the components have the same values in any coordinate system. Levi-Civita tensor is a type 0,4 tensor, and is defined as follows. It's usually given the symbol epsilon, so epsilon mu nu alpha beta is equal to plus or minus the square root of minus g, that's the determinant of the metric, if these indices, mu, nu, alpha, and beta, are an even or odd permutation of 0, 1, 2, 3. So even goes with the plus sign, odd goes with the minus sign. And if these indices are not a permutation of the numbers 0, 1, 2, and 3, then it's equal to 0. So 0 otherwise. Notice that the Levi-Civita tensor is totally antisymmetric. Meaning if I swap any two of the indices, I pick up a minus sign. So for example, if mu, nu, alpha, and beta is an even permutation of 0, 1, 2, 3, then the value is plus square root of minus g. So then if I swap, say, alpha and beta, then it becomes an odd permutation and I pick up this minus sign. So epsilon mu nu alpha beta is equal to minus epsilon mu nu beta alpha. I could also swap the indices nu and alpha and again switch the permutation from even to odd or from odd to even and pick up a minus sign. I could also write epsilon mu beta nu alpha. Now in this case, to get this index pattern, I've had to move beta. I've had to switch beta with alpha and then switch beta with nu. So there are two pair interchanges, so there are two minus signs. So this is a plus sign here. So these are the components of the Levi-Civita tensor in some unbarred coordinate system. What are the components of this tensor in a barred coordinate system? Well, we can work that out explicitly. Epsilon bar, let's call the indices mu1, mu2, mu3, and mu4, is equal to partial x alpha 1 with respect to x bar mu1, partial x alpha 2 with respect to x bar mu2, partial x alpha 3 with respect to x bar mu3, times partial x alpha 4 with respect to x bar mu4, all of that times epsilon alpha 1, alpha 2, alpha 3, alpha 4. Now on the right hand side we have a sum over the repeated index alpha 1 as well as sums over alpha 2, alpha 3, and alpha 4. So there's a quadruple sum here. So there's lots of terms, but most of those terms are 0. They're 0 unless alpha 1, alpha 2, alpha 3, alpha 4 is some permutation of 0, 1, 2, or 3. So this is equal to, for example, if alpha 1, alpha 2, alpha 3, alpha 4 is equal to 0, 1, 2, 3, then this is partial x0 with respect to x bar mu1, partial x1 with respect to x bar mu2, and so forth. Partial x2 with respect to x bar mu 3 and partial x3 with respect to x bar mu 4. And that will be multiplied by the value of epsilon, which is square root of minus g. And we also have in this quadruple sum odd permutations of 0, 1, 2, 3, and they'll be multiplied by minus the square root of minus g. So here's the minus sign. And now let's swap the 0 and 1 indices. So this is partial x1 with respect to x bar mu 1, partial x0 with respect to x bar mu 2, partial x2 with respect to x bar mu 3, partial x3 with respect to x bar mu 4, and so forth. All of that times square root of minus g. So we have in here all of the possible even and odd permutations of 0, 1, 2, 3 appearing in the numerators. Now let's take a look at these free indices, the mu's. Let's say mu1 and mu2 are both equal to 0. Then this factor, partial x0 with respect to x bar 0, is the same as this factor. This factor is the same as this factor. So these two terms inside the curly brackets cancel. And in fact, every term inside the curly brackets will cancel pairwise if any of these indices are the same. So the only case in which we get something non-zero is when these four indices are distinct. So there's some permutation of 0, 1, 2, and 3. And if they are a permutation of 0, 1, 2, and 3, if you remember your linear algebra well enough, you'll recognize what's in the curly brackets is just the determinant of the partial of x with respect to x bar. So this is equal to epsilon mu1, epsilon bar mu1, mu2, mu3, mu4 is equal to the square root of minus g times either plus or minus the determinant of partial x with respect to x bar if mu1, mu2, mu3, mu4 is an even or odd permutation of 0, 1, 2, 3. So even goes with plus sign, odd goes with the minus sign, and it's 0 otherwise. Now let's look at the way the metric itself transforms. We have g bar mu1, mu2 equals partial x alpha 1 with respect to x bar mu1, partial x alpha 2 with respect to x bar mu2 times g alpha 1 alpha 2. And now let's take the determinant of both sides. The determinant of g bar is just, we denoted g bar. And remember, the determinant of the product of matrices is just the product of the determinants. So we have two factors of the determinant of partial x with respect to x bar times the determinant of g. And now multiply by minus 1 and take the square root. And we have square root of minus g bar is equal to determinant of partial x with respect to x bar times square root of minus g. By the way, I'm assuming that the determinant of partial x with respect to x bar is positive. So we're assuming that both the barred and unbarred coordinate system have the same orientation. They're both either right-handed or left-handed coordinate systems. So now notice we have square root of minus g times the determinant of partial x with respect to x bar here, which is precisely square root of minus g bar. So what we conclude is that the Leviathan tensor in the barred coordinate system is just equal to plus or minus square root of minus g bar if mu1, mu2, mu3, mu4 is an even or odd permutation of 0, 1, 2, and 3, 0 otherwise. So in any coordinate system, the components of the Leviathan tensor are defined by plus or minus the square root of minus the determinant of the metric in that coordinate system if The indices are an even or odd permutation of 0, 1, 2, 3. So that's the Leviathan tensor. It appears in quite a few contexts in relativity, and I think we'll see some of those uses in later lectures.